Hi guys. Since it was requested, today I will talk about the active clamp forward converter. So, first of all, what is a forward converter? You know that you start with the buck converter, which is of course this. Then you ask how it is possible to make this converter isolated, and the answer is basically to use the forward converter. Now, the classical forward converter is this: the input capacitor, the transformer, the switch here, and another transformer for the recycling with the diode, another diode here to recycle the inductance, and the transformer with the secondary. These two diodes here ensure that all the transformer never saturates, and then you have the inductor with the C group at the output. So basically, in the classical forward converter, this inductor L is the same as the inductor L of the buck, so it has to be designed. This inductor here as a waveform like this, and this node here as a waveform like this, like a buck converter actually should. Now, the problem with the forward converter is that this switch here has a lot of stress. So basically, the stress of the switch is VDS. It is equal not only to Vin, but also the reflected secondary voltage on this point here, which is the ratio N times Vin. And you can add even the spikes. So basically, the VDS is more or less 2.3 times the Vin. This can put a lot of stress on this MOSFET here, and for this reason, the forward is used in 100 watts, maximum 200 watts application with a low input voltage. Now, the problem of this configuration is that these diodes dissipates a lot. And so the first thing that we are going to do is to eliminate this and this by putting an active clamp. The active clamp can be realized with a PMOS or NMOS. I think that the PMOS is the easiest one, since it is low side. Then, once you selected the PMOS Q1, you put a capacitor here and connect it to here. This capacitor C must be way higher than the CDS of the PMOS. Otherwise, you're making a capacitor divider at this point here, which you don't want. Keep in mind that the transformer converter here, the forward transformer, which is this, is a real transformer. So, the magnetizing inductance, which I will draw in blue, which is in parallel with the transformer, LM, must be as high as possible. So if you put values like 1 micro to simulate this, the simulation won't work. This inductance will exhibit the same behavior of the inductor L of a flyback converter, and this node here will start to ramp up, basically by destroying the switch. So this is the introduction of the forward converter, and now we will skip to the SPICE simulation. We will start by adding the input voltage at 12 volts. So now we expect the stress to be around 40 volts. Then we put the bulk capacitor of 10 micro. Remember that this is basically useless unless you put a resistor of 1 milli here. A capacitor in parallel with a constant voltage does not produce any result in LTSPICE. So now what we want to do is to realize directly the forward converter with an active clamp. You can find the forward converter in another of my videos on the channel. Let's show the phase dot and let's pair them with the command k L1 L2 equal to 1. And remember that this is not the turn ratio, but just the coupling factor. To realize a real transformer, you have to put values as high as possible. So you can't put just 1 micro, but values like 1 millihenry. So this is a real transformer. We also add some parasitics like the ESR, which can be 10 milli, and also the inductor here, the magnetizing inductor, which has to be, of course, put in parallel to this configuration. This inductor is LM, and it has a reasonably high value, like 100 micro. If you don't believe me, just search on some paper online, but a true transformer has magnetizing inductance very high. In the flyaway transformer, instead, the magnetizing inductance is designed, so it can have very precise values like 10 microhenry or something of the sort. Now what we want to do is to add the first MOSFET, NMOS. Let's select the IRF 400 and 03. This MOSFET is good because it has low iron resistor and a very low gate charge. This will ensure that the simulation can work also at higher frequencies without causing too much problems. We will start by adding the 2 diodes here. And then we will use an inductor with a reasonable high value, like to 22 microfarads. I already did the design on paper, and this value are enough. Let's put a load of 1 ohm and an output voltage with a node out. The node of interest are the output voltage and also the switching node voltage, which is this. Now we need to drive the NMOS and to also add the active clamping with a C capacitor. To use the active clamping, as I said before, you have to use a PMOS if you want it to low side it. You have to know the CDS capacitance of this MOSFET. I checked the datasheet, and if you pick the IRF 96C, this will work if you put a capacitor way higher than his CDS, in this case 470 nano. As a rule of thumb, you can start with 100 nano and then increase the capacitance if it doesn't work. Now it's time to drive these 2 MOSFETs, and for me this is the hardest part, because it is not so straightforward as you may think. Let's start by doing some parameters, the dead time 10 nanoseconds, and also the duty cycle equal to 0.45. Then we'll select the switching frequency to 250 kHz and the switching period as the 1 over the switching frequency. It's time to use the pulses. So this is G1 and the other will be G2. They are both low sides, and so we don't actually care about putting them. Okay, so the pulse of the high side is the main switch, so the initial voltage will be 0 and the on voltage will be 5. Now the rise time and fall time you can put 1 nano, it won't change a thing. But for the on period, use always d over fs, or d time ts. And the period will be, of course, ts. Now, since you want the dead time in a synchronous configuration, just write minus td, and you are fine. Now, we ask a question. Where or when the transistor M2 should be active? Because that's the difficult thing to understand of this circuit. So let me pick some waveform. Let me pick paint and draw some waveform. If this is the VGS of the main MOSFET, so VGS 1 between 0 and 5 volts, the other MOSFET, the VGS 2, remember that this is a PMOS. So, not only you have to translate this by a quantity by his t period t on, which is d times ds, but you have also ensure that during the on period it must go to minus 5. So the waveform should look like this: 0 here and minus 5 when you want to be active. Remember that there is also the dead time dd on both sides. So this is what it will look like. To replicate this, the best way that I did was to put another pulse identical to this, with the only difference that the delay is, of course, d times ts, and the on period is 1 minus d, because it is a complementary waveform, and the on period is minus 5. In this way, you are creating not only a voltage which is complementary to the other, with the d times ts delay and 1 minus d on period, but you're also creating a good voltage for the PMOS to work, since it will need a negative voltage here. If we run the simulation now, it should work without too much problems. So let's run the simulation and see what happens. The first thing that we're going to check is this voltage here. As you can see, it is not exactly 20 volts because I put the resistor of 1 milliohm. This will ensure that this capacitor is really useful and not shorted to nothing. So as you can see, you have some spikes on this capacitor here. The other node voltage that we want to check is this. The primary node voltage of the MOSFET, the VDS, must not increase, otherwise it will destroy the MOSFET. If we check, as we can see, the stress is kept to 2 times the input voltage, which is correct in a forward converter. If I decrease this inductor here to 1 micro, what will happen is that this voltage will increase to value which make no sense, like this. So I have a stress which is not compliant to the forward converter. You can't even call this a spike. So you have to put a very high value of Lm in order to make it work. After a transient, it will stabilize. Now, another aspect of this is that the voltage of the capacitor C3. The voltage of the capacitor C3 should have a ripple alongside it. It is perfectly normal, since it will... yes, so it is normal because it is charging, discharging at each cycle. Then the switching node, it looks perfectly fine to me, and the output voltage should be set to more or less half of the input voltage. I put a duty cycle of 0.45, and since the tune ratio is 1, you can understand that this result is reasonable. to have 80 volts. Most of this voltage here, it is lost because of the diodes. You may think that this voltage can improve by also adding a Schottky diode, which is partially true, but in reality, you have to change the forward voltage. You have to change these diodes to active MOSFETs. So, the only thing left to do here is to change these two diodes to MOSFETs. It is not easy, but it can be done. In the next video, I will show you how to avoid that this voltage here goes to 2 times the input voltage. There is another topology which is called two switch forward. This is very useful because it puts a switch here. This is the transformer, and the other switch. No, it was not like that. But basically, the two switch transformer, the two switches forward, it can clamp the voltage to V in. It is very useful, and I will do it in the next video. For now, let's focus on how we can improve our forward converter by cancelling this two diode here and putting the MOSFET. So naturally here, the MOSFET which will go is the NMOS, because it is low side and you can do it without any problems. Sorry, before talking the MOSFET, another consideration. To understand how to select how to select the interval in which the MOSFET should be active, we have to understand perfectly when the D2 and D1 is active. Of course, one is active in the on period and the other in the off period, but we have to understand perfectly who and why. So let's select the current of M1. Toggling the fact that this current is absolutely very clean, I am very impressed. Let's select the MOSFET D2. As you can see, D2 is active in the off period, and D1 is active in the on period, meaning that D1 can be active when the MOSFET M1 is active, and D2 of course the same. So D1 and D2. Let's substitute this. You can even stop there, okay? You could even stop there, because this is an already active clamping forward converter. You can even stop there, but I can show you also this before closing the video. So let's cancel the first diode and let's put an NMOS. The easiest way here it is to put the NMOS, because it has the low side configuration here, and so there shouldn't be any problem to connect this guy to the D1, D2. It was D2 was there, and D2 is active in the off period, so D2 must be connected to the off period, and D1 to the on period. Yes, okay. So this is the on period. I don't want accidentally to connect them to the contrary. D1 is the on period, yes, okay. And you can toggle this and put the NMOS to here in series with the transformer, but it is easier to put the MOSFET here, since it is connected to the ground, and by doing so, naturally it is better, because you have an already grounded source, and so you avoid the problems of high side driving. Let's put this. And let's put the same voltage here, but naturally with a translation of D times Ts. And here 1 minus D. If we do run the simulation, we should obtain the same results. If we... okay. There is another concept. There is a misconception here. If you move the MOSFET, before it was right if I had substituted with the PMOS, but this time I am saturating the MOSFET. So now it is the contrary, because if I wanted to do in this way, I had to put a PMOS in the high side, but I have to invert them. Okay, now it's correct. Sorry for this. I am increasing the spikes because naturally I'm putting more hard switching. Okay. No. I didn't put the dead time. No. The dead time is there. So I'm increasing the spikes because let's try to increase the dead time, but I don't think that we can avoid these spikes. Okay. So if we increase the dead time, we can avoid the spikes. Good to know. So the dead time was not high enough to decrease the spikes here. Okay. So good to know. Now the output voltage has increased definitely a bit. As you can see, we have 8.75 volts in the diode configuration, in the MOSFET configuration. In the diode configuration, we had 7 dot something volts because, of course, there was the diode drop. Here the situation has not changed, of course, and here the situation has not changed either. You can notice the dead time here. If you zoom enough, you can notice the dead time in this interval here, because when you have the dead time, the body diode is conducting, and so you have minus 0.7 volts. And as you can see here, you have an interval of 24 nanoseconds, which is more or less the time that I put. No, to be precise, the dead time is only... okay, it is only this, the dead time, to be more precise. But by the way, we have improved the circuit a lot. So now the output voltage is very, very near to 10 volts, as we actually expect it to be, because the duty cycle is kept to 0.45. If I put 0.49, we should have a voltage which is very near to 10 volts. And as you can see, we have almost succeeded into doing this. The reason why is not because first there is the dead time, and second because there is the drop voltage of this ESR, which of course does count. So I think that we obtained a good forward converter with a near voltage duty cycle expectment. And now I think that we can close the video with this configuration here. And I hope that you understood everything. Sorry for the mistake before. And I will see you in the next video with the two switch forward converter. Thank you guys, and see you in the next video. Bye bye.